Test for independent samples, chapters 10 and 12. Example, in a sample of N1 equal 13 smoking areas, the mean carbon monoxide level X1 bar 12.6 parts per million with a standard deviation S1 8.1 parts per million. This sample is taken from a larger population of all such areas with unknown mean and unknown standard deviation. We want to compare it to a sample of N2 equal 9 non-smoking areas where the mean carbon monoxide level X2 bar is 7.3 parts per million with standard deviation S2 of 1.9 parts per million. And this is taken from the population of all such areas with unknown mean and unknown standard deviation. We're going to assume the carbon monoxide levels are normally distributed and use Welch's method with 90% confidence. So that means that 1 minus alpha is 0.9. That's our level of confidence. Our level of doubt, alpha, is 1 minus 0.9, which is 0.1. Alpha over 2 would be 0.05. We want to test H naught, null hypothesis. The means are the same. mu1 equal mu2. Carbon monoxide levels are the same versus the alternative. HA, mu1 is not equal to mu2. Carbon monoxide levels are different in smoking versus non-smoking areas. First step is to compute the degrees of freedom, which would tell us which row to look at in the t-table. And it's kind of a complicated formula. S1 squared over N1 plus S2 squared over N2 and the whole quantity squared. And then do S1 squared over N1 and square that, divide by N1 minus 1. S2 squared over N2, square that, divide by N2 minus 1. Add those two numbers and then divide. Let's see if we can do these. So it's 8.1 squared. 8.1, and then we want to square that. Divide by, oops, I did a plus. Okay, let's clear this out. 8.1 x squared divided by 13 plus 1.9 x squared divided by 9. We're following order of operations. We're doing what's inside parentheses first. And then if I push equals, that'll compute everything that's inside the first set of parentheses there. And then I want to square that. So I'll push x squared and equals, and I get 29.68 something. And I'm going to store that in memory. That's our numerator. That's dou and equals. Okay. And now let's work on the denominator. The bottom left, we have 8.1 x squared divided by 13 equals about 5, and then we want to square that and divide by 12 equals, and I get 2 something, 2.1 something. And I'm going to store that in memory. I'll go store it in memory B, go over to memory B. And then the bottom right is 1.9 x squared divided by 9 equals, and then square that and divide by 8 equals 0.020 something. And I want to store that and I'll put that in memory C. Okay, so this is what we have so far. We have the numerator 29.68 something, bottom left 2.1 something, and then 0.02 something. And I want to add those. So I get, I already have the 0.02 showing. I'll be plus second recall and go over to memory B equals 2.14, so that's our denominator, and then I'll store that in memory B, or I don't need the other number in memory B anymore. And then I want to divide the numerator by the denominator. So if I do second recall divided by second recall, go over to memory B, equals, get 13.85 something. So that's our that's the result of our computation. And then we want to truncate the decimal. So we just chop off everything that comes after the decimal point, and that gives us 13 degrees of freedom. So we want to, that tells us the row of the t-table. So now we want to look in the row 13, and alpha over 2 is 0.05, so it's column 0.05 of the t-table of the appendix to get the upper critical value of 1.771, and the lower critical value will be just the opposite of that, put a minus sign in front, negative 1.771, because the t distribution is symmetric. Okay, so then we can also, so that's our value from the t-table, and then we also want to compute the t-score, or the test statistic. So it's the difference of the means divided by the square root of the variances. So you plug in the numbers. 12.6 minus 7.3 is 5.3, and then square root of 8.1 squared over 13 plus 1.9 squared over 9 gives us a 2.3 something, and divide, we get about 2.271 approximately. So because our test statistic of 2.271 is more than the upper critical value of 1.771, we reject H0 with 90% confidence, include the carbon monoxide levels are different in smoking versus non-smoking areas. Also, we can go a little bit further with this. Because our test statistic is between the 0.01 and the 0.025 columns of row 13 in the t-table, the p-value has to be between 2 times 0.01, which is 0.02, and 2 times 0.025, which is 0.05. And according to this chart below, between 0.01 and 0.05 indicates moderate evidence. So the sample provides moderate evidence that the carbon monoxide levels are different in smoking versus non-smoking areas. Okay, a couple of things to note about Welch's test. Each variable must either be normal or the sample size must be at least 30. That's one thing to note. Also, there is a shortcut. It's this formula for the degrees of freedom was rather complicated. There is a shortcut. You can take one less than the sample size, so the smaller sample size. So the smaller sample size is 9 minus 1 is 8. And instead of looking in row 13 of the t-table, you look in row 8. The disadvantage here is going to increase the probability of a type 2 error. So it's not as accurate as the way we did it, but it's a lot shorter. Another note, if the population variances are either known or known to be equal, different procedures can be used which reduce the probability of a type 2 error. However, in practice, usually the population variances are not known. Okay, part B, we can also test whether the standard deviations are the same or different in smoking versus non-smoking areas. First step is to compute the test statistic. That's going to be S1 squared divided by S2 squared. In this case, it's 8.1 squared divided by 1.9 squared, which comes out to be about 18.17. And because S1 is in the numerator degrees of freedom are N1 minus 1, which is 12. The denominator degrees of freedom are N2 minus 1, which is 8. So to get the upper critical value, you want to look at in the F table, and it depends. It could be, I wrote the 0.05 page. It could be the 0.05 page or row. It could be, depends on how the table is set up. It might be the 0.05 row, and this could be a row group. sometimes the row group. It might be a row group instead of a row there, and the column 12 to get the upper critical value of 3.28 approximately. And because our test statistic is more than our upper critical value, we reject H0 with 90% confidence and conclude the standard deviations are different in smoking versus non-smoking areas. And just a note about this, because we put the larger sample variance in the numerator, there's no need to compute the lower critical value. Another note, to use the f-test, each variable must be normal. Part C, test of the variances. This is actually the same test as the test for the standard deviations. It's going to be the same conclusion. And that concludes this presentation.